Our project is the Distributed Sound Event Location System, also known as DIESEL. In this group, we have Mark Judy and Drew King on the software team, and Brandon Laguerre and Kristen Tana on the hardware team. These are the project requirements. It must be able to identify the originating location of the sound event within 5 meters. It must be able to verify the sound is being analyzed from all sensors with greater than 90% accuracy. It must be able to identify what originated the sound event with greater than 80% accuracy. It must be able to analyze the location and label the sound event within 5 seconds. Have a minimum required distance between sensors of less than 5 meters and a maximum operating distance between sensors of greater than 100 meters. It must be able to determine the temperature of the environment within 1 degree Celsius. It must maintain a sensor weight of less than 5 pounds. It must have a sound event capture range of greater than 100 meters. It must be able to achieve an IP rating for the sensor greater than or better than I-45 IP. It must also maintain a cost of less than 500 US dollars.
Hi, this is Mark, and I've been mainly working on the programming for getting audio data onto the central server for processing. As you can see, this is the Teensy code. Currently, the way that the project is set up is we have a mic connected to the Teensy. The Teensy is sending the data to an ESP32 using SPI, and then the ESP32 is connecting to Wi-Fi and then connecting to a central server that I have set up. This is the TT code, however. It's pretty simple to set up. It's mostly Arduino code. Basically, there's a little bit of setup. I do some audio setup and then start SPI. And then I just run this loop several times, or it keeps running forever. Whenever there's an audio block available, it sends the block over SPI to the ESP32, and I have a function here that is creating a hash code so that I can verify that the audio is not getting corrupted from the TNT to the ESP32, and it's being filtered at about 1 out of every 250, assuming that the data is completely random. But that's just so that we don't print way too many times. And then on the ESP32, the ESP32 code is much more complicated. I'm using the ESP IDF libraries, and both of these are in C++, by the way. But basically what happens is the ESP32 does some initialization. It initializes SPI, and then it connects to Wi-Fi very quickly. We have the default SSID set to my Wi-Fi SSID, as well as the password set to my Wi-Fi password so that the ESP32 can connect. And then after that, it basically runs in a loop. Well, it connects to the node server that I have set up, and then runs the loop, basically receiving an audio block over SPI and then sending it to the server immediately after. And I have the same hash code that is printing to make sure that the audio is not getting corrupted. Then on the server, this is still a work in progress. The hash code function is the main problem, but that's a pretty basic function. The server's using TCP sockets to communicate. TCP is pretty fast, and it prevents corruption. So um, currently the server's pretty small. It's very simple, but uh, I'm working on verifying that the audio data is not corrupt before I continue anything else. Um, the main problem with this is that uh, JavaScript and TypeScript don't have the same types, number types as C and C++. So uh, the hashing codes are not quite working properly, but I should be able to fix that quickly. Um, as a demo, I can show it running. So this is the server launched, and then I can start the ESP32. So I got a message from the ESP32 on the server, and then I can start the Teensy. So as you can see, the audio data from this is the serial uh, line from the Teensy, and this is the uh, output from the ESP32. The audio hashes that are getting printed out match, um, and they're getting printed out at a rate of about once every half a second. Um, but there's a problem with the hash code function on the server. Uh, it's clearly receiving it's receiving a lot of data, but it's not quite printing or converting the creating the hash codes properly. So uh, this is printing out garbage currently, but that should be fixed quickly.
Currently, the server and database for our web application is being run locally. The node server establishes a server connection as seen in the lower right corner, and a connection to a local Mongo database. Since the front end is still under development, this shows the server being fed a hard-coded user information that will then be stored in the database. As you see in the lower right terminal, the data has been fed to the server. The user's password is also being encrypted with the utilization of bcrypt. A Mongo shell command is then being run in the top right terminal, showing the new user being populated in the database. The database's schema is shown in the sound events and user models. Our classification model continues to be developed in the attempt to increase the accuracy and the number of different classification sections it can predict between. TensorBoard shown on the right is currently showing the training data for all the models that have been attempted so far. This graphical view can also help while training by helping monitor for overfitting while training. The lower left corner shows a file of all the testing results for each model that has been trained so far. The model that will be shown training is the model that has performed the best so far. This model comprises of 5 convolutional layers consisting of 64 nodes in the first layer and 128 nodes in the other layers, and no dense layers. To combat overfitting, a dropout of 25% has been implemented between each of the convolutional layers and a 40% dropout at the end of all the layers. Tensorboard can then be utilized to show the training progress graphically. After the conclusion of training, we can see the model is performing at 73.5% accuracy with a loss of 1.1. The training and tweaking of the model's makeup is continually being developed, with the hopes of increasing its accuracy. With this model, it is able to classify 10 different bird species calls at an accuracy of 73.5%.
After initially setting up the PCB, we uploaded a code that would blink its LED every once in a while to test to make sure that the microcontroller actually works as intended. Here, we're going to test the audio module on the PCB by using a fast Fourier transform algorithm. Determining the location of the sound is a major aspect of this project. To help us do this, we have a GPS module, which uses the Neo 6M chip, its antenna. Unfortunately, at the current moment, the GPS module isn't receiving satellite data as intended. This is going to be one of our major areas of focus in the future for the final project.
This is the solar charging circuit. When the solar panel receives light, you can tell the batteries are charging because of the red LED. When the batteries aren't charging, the LED will turn blue. The PCB can be powered through the USB cable. Shown here is the 5 volts from the USB cable. Now the 3.3 volts after the voltage regulator. And the 3.3 volts after the ESP32 voltage regulator. The PCB can also be powered with batteries, shown here. The primary MCU is designed to communicate with the ESP32 through SPI and serial. In order to program the ESP32 through a serial connection, the I/O0 pin needs to be grounded, and this is done through the code of the primary MCU. This code shows the ESP32, scanning for available Wi-Fi networks. Each time data is received, the LCD LED will blink.